Hello everyone, and welcome back to the C-Squared channel. Physics has evolved dramatically in the last few centuries, from the first theory of gravity developed by Sir Isaac Newton to the modern problems involving dark matter and dark energy. As a result of this evolution, there are major pillars that make up our understanding of physics. That is what I'll be discussing today. Physics works very differently at different scales, and each needs their own theories to make them work. There are two things we must consider when understanding what branch of physics to use: the size of a system and the speed it is moving at. These are then split into four separate squares on this grid here. The first of these, which is on the top left, is also the oldest in the grid, is classical physics. This branch of physics works for very large scale objects, or you could say for macroscopic objects, such as humans, machinery, planets, and even galaxies. But the speeds at which you work with should be far, far lower than the speed of light. So we're talking like, usual speeds of a car, which is probably at most maybe 100 kilometers per hour, you could say. So the foundation of classical physics stems from quite far back to ancient Greeks, and also in medieval ages. They created concepts of inertia, acceleration, and forces. These all being discovered separately by completely different people across the planet. It was only until Sir Isaac Newton who was actually the first to unify a lot of these concepts to form the foundation of classical mechanics. And we know these as his three laws of motion that we all continue to use to this day when dealing with macroscopic objects. These are great, explain a lot of human scale motion. So as an example, we could talk about how a person would move, or what kind of forces you would have if you were to push it onto an object. And they can also be used to describe projectile motion, such as throwing a stone over a pond, or firing something out of a cannon. They've also been expanded on to explain the motion of planets using Newton's universal law of gravitation, which is shown here, and Kepler's laws of planetary motion, which gave us an understanding of how the motion of our solar system works. As we can see now why there are planets that are orbiting around a central star, for example. So branching on from this, further developments in classical physics gave rise to the concepts of electromagnetism, thermodynamics, material science, and even fluid dynamics. There's quite a lot of branches that I can go into there, so I'm not really going to go too much into a lot of them, but I'll be briefly talking about the first two areas. Classical electromagnetism made the foundation of a lot of modern technology we have today, thanks to James Clerk Maxwell's equations of unifying the phenomena exhibited by electric and magnetic fields as observed by other scientists at the time. So what these kind of, what do these phenomena involve? Well, they include things like electromagnetic induction, which can be described by Faraday's law, which is how electricity can go through a coil as you pass a magnet through it. So, if you have the coil of some material, and you pass a magnet inside, you move it through, it will induce a current into the coil because of the changing, magnetic field. So that's something that can be described through Faraday's law of magnetic induction. There is also Ampere's law, which states that magnetic fields always curl around a rod that has electrical current flowing through it. So, take this diagram here. If you have the rod coming down, infinitely long, you can see that it actually creates these little circles, these little rings of magnetic fields, and that's the curl. You call it a curl around the rod. So that's what Ampere's law describes, is just which direction the magnetic field is moving in. So all of these were unified with Maxwell's equations, and a lot of these have later led on to the development of electrical circuits, of which you would have certainly have probably seen or used, and if you were you probably would have definitely seen this at school, because you have your resistors, bulbs, batteries, and whatnot. You know, you got all these different circuits, diagrams that you do at school. So, in terms of classical thermodynamics, though, the development of this field explained a lot of phenomena involving engines and heat properties of gases and other states of matter. So it's mostly just focused on heat, really, like, you know, temperature, heat energy, all that kind of thing. So the development led to the laws of thermodynamics, which forms this, you know, this is the foundation of this part of classical physics. This branch involves looking at the thermal properties of systems. We have a huge range of different energies. You know, just to list a few, we got things like internal energy, Helmholtz free energy, Gibbs free energy. We got a lot of stuff, you know, and you know, they all work with ideal gases as well. You can put them up with an ideal gas, which is, you know, a gas that it can be easily compressible. You could just compress it forever, pretty much. It's very ideal, literally in the name, so it doesn't exist in nature. But because of that, a lot of these thermodynamics, concepts were expanded further to resemble that of a real compressible gas that would actually exist in nature. So that's why we have things like the Van der Waals forces and, you know, all that kind of thing. So, I mean, yeah, this is sounding pretty good, right? You know, all these different types of fields in classical physics, it was having quite a good run. It's been able to explain a lot of things that were going on in nature. Everything was working pretty well, and everything was looking pretty nice and dandy. But then a new model of the atom was developed, and that pretty much destroyed everything. Okay, well, I mean, that's exaggerating a bit. We can't really say that, but this is when the flaws and limitations of classical physics actually really started to show. It was found that some of the discoveries regarding atomic scale phenomena could not be described by classical mechanics principles, such as, you know, the new model of the atom that was being found at the time. So we're talking like early 20th century, like 1910s, you know, somewhere around that period. So this is when it was first discovered that an atom consists of a nucleus in the center with electrons orbiting around them. So that's when we first discovered that it's not just a ball of charge with some tiny little thing stuck on it, you know, as you know, that would be the plum pudding model. That's now obsolete. We don't use that anymore. We're now moving on to this kind of model. So if we're using pure classical mechanics, what we'd find is that the electrons would actually eventually fall into the nucleus as they lose energy through orbiting, which is, you know, as described with Kepler's laws of motion and standard, you know, circular motion mechanics. This clearly isn't the case. We know that. If this happened, then, well, obviously all matter would probably have been gone an extremely long time ago. Somehow, they are managing to stay in place, and they couldn't figure out why with classical mechanics. It just could not explain it. There's also another interesting situation where you have beams of electrons, which at the time they were called cathode rays, I assume. So they had, you know, wave-like properties, which could not be explained through classical wave theory, you know. So what I mean with this is, you have a beam of light, you pass it through a little slit, and then the light kind of just splits out, and you have this cool little pattern, right? That's interference. But it was found that beams of electrons also had the same thing, even though they are particles and not waves. So this is a really crazy moment, and you can't really describe that with classical mechanics at all, or classical physics in general. That development became later known as wave-particle duality. So that's kind of like a future thing there. So all these problems that classical physics had, they actually contributed to the development of the next quadrant on the grid, which is on the bottom left corner. This is quantum mechanics, or quantum physics. This branch involves explained principles that are at extremely small sizes. We're talking atomic and nanoscales here. And the speeds you work at are still much slower at the speed of light. So that's a thing to note there. That's why it's on the bottom left. So this is one of the two pillars of modern physics, as this was being developed in the 1920s. and solves a lot of the problems that are faced with classical physics, which is, where you would apply this to really small stuff that just could not work. So an example of solving this is the atomic model, as we have said. So this is solved with Niels Bohr's model of the atom, and this says that electrons do in fact still orbit around the nucleus, but they do this at discrete levels, meaning that they stay in the same orbit and they do not change where they are, And the reason why they stay in the same orbit without falling into the nucleus is because they are constantly emitting and absorbing radiation from the surroundings, and that's why they keep staying in their same spot. So, quantum mechanics led on to a whole load of new theories about how particles behave at the really, really tiny scale. And this also introduced the legendary Planck's constant H, which is a fundamental constant that forms the basis of a lot of quantum physics. Now, if you went on to study this kind of thing, you'd probably just be seeing H all the time. You'd never stop. Like, H just appears everywhere. And I know this from experience, so gotta take my word for it. But, as a side thing though, they also took part in the change of redefining the 7 standard units that are used in physics. This happened in May of 2019, so this is very recent things. It hasn't even been a year yet as of making this video, actually. So that's just another cool thing that it was used for. But the whole point of quantum mechanics, though, is that it says that a lot of quantities are discrete. A lot of, energy is discrete, as we've seen with the Bohr's atomic model. A lot of things are discrete because of the Planck's constant H. Everything is kind of like a multiple of H, in a way. And it's hence why this field of physics is called quantum mechanics, because quantum is quanta. It's, it's like one unit, you could say. So everything's got distinct values. An example of this, as I've said, is the energy levels of Bohr's atomic model. So like different levels at which an electron can stay in. That's an example of that. And another one is the electric charge of an object, which you could say is always in multiples of one electron. So the developments of quantum mechanics led to very advanced technologies as we have today. We now have on our phones, we have touchscreen phones, and this is because of quantum mechanics. They use quantum tunneling, and that's something I want to touch upon in a future video, actually, so this is something to keep in mind. We also have new sources of power, even. As seen with, we have nuclear power plants in, the few countries that actually can do nuclear power. So these utilize quantum nuclear theory, for example, yeah. So, let's go back to classical physics real quick. So we can go a different direction now. We're not going to go down to the very small. We're now going to go to the very fast. And this is where we can see another area where classical physics has failed. So let's recall the equation for classical kinetic energy. So it's just the energy from moving around. And it's given by this equation here, right? M is the mass of an object, and V is the speed it's moving at. Okay. So for large-scale objects, at very slow speeds, this equation holds up very well. It works, that's why it's taught in the school, because it's kind of like a foundation equation. But what if we want to go to the speed of light? Well, we all know that nothing can go at the speed of light except for, light itself, hence why it's speed of light. And nothing can go faster than the speed of light for sure. So if we were to plot out this relationship with the velocity at the bottom, right, and the energy on the y-axis, we would see some kind of interesting plot here. So we would see this is a typical quadratic curve. We can see that. But we would see that when we reach to the speed of light, there is actually a value for energy. So this just implied that you can actually achieve the speed of light if you travel at this certain energy. We know experimentally through through experiments in CERN, the particle physics lab in Switzerland. We know that this clearly cannot be possible, can't be achieved. They could get incredibly close, but the energies are way higher than what this graph would show. So it cannot be true. So this is another major flaw by assuming this equation for incredibly fast motion. So this is to be solved with Albert Einstein's theory of relativity, which goes right up to the top right corner of the grid and is the second pillar of modern physics. So this branch looks at human scale and astronomical objects that reach speeds near to the speed of light. And all phenomena in this case you could say are relativistic. So there are two parts here. It can be split into special relativity and general relativity. What I've talked about with the equation there, the energy equation, this is special relativity. So, this was solved by having something called a Lorentz factor, which, this kind of goes into a bit of detail, but I'm not going to go into it much. But the Lorentz factor is essentially the reason why, how we can have this restriction of going to the speed of light. So we could transform that equation into something else. So, special relativity pretty much, looks at how objects behave near the speed of light. And they introduce concepts of something called time dilation and length contraction, which are two pretty much foundation parts of special relativity that I won't go into here, but just know that they exist. They're things. And that happens because the speed of light stays constant everywhere. No matter where you're looking, no matter what you're doing, speed of light is always constant. That's a must. And then you got general relativity, which looks more at the way the universe looks, and it also exists as a modern approach to the theory of gravity. So that's kind of our best bet in understanding what gravity is through general relativity. But again, that goes quite deep, so I'm not going to go into that in this video. But it's just something to keep in mind. So, with these quadrants in mind, things seem to have settled. We now have new theories that can explain phenomena where classical physics failed, and we ended up developing a lot of new technology that can aid us. We have it feels like now we've solved everything, right? We have all these really crazy technologies. We've got all these smartphones now. We have, it's just crazy. We've got all these nuclear power plants, and it is mad. But in more recent times, and we're talking like just a few decades, we're now faced with a new problem. So, there are 4 fundamental forces in the universe, and we have only been able to unify 3 of them, which are explained by quantum mechanics. And then gravity is the 4th one that's just left with relativity. So this new problem now is, well, can we unify the forces explained by quantum mechanics and gravity from relativity? So this is a really big challenge, and this is still ongoing. So the result of this probably will lie in the 4th and final quadrant of this grid. The current theory that is aiming to do this is called quantum gravity, and that's what this part is. So this field would be looking at, relativistic speeds. So this is speeds near to the speed of light, but also at sizes that are at the atomic scale. So that's why it ends up on the bottom right corner of the grid. And this is something that hasn't quite been achieved just yet. They're working on it. Things are coming through, but it's still quite a long way. But if this can be done, then we basically have a theory of everything, which can describe how all the 4 fundamental forces behave at a small scale and near light speed, but still very much in progress. So here we are. The pillars of physics can simply be summarized with this single grid, showing how theories have evolved from classical physics on the top left to the 2 branches that were heavily developed in the last century at the bottom left and top right, to the future, where these 2 modern physics fields can be unified further to give us this idea of quantum gravity, which would probably help with developing even more things, can help even understanding more about the universe itself, and, it could even explain what dark matter, dark energy even is. But it's still all very much unknown, and we have to kind of reach that point first to know what's going on. So, thank you guys so much for watching. I'll see you all in the next video.